Hello folks, StylePoint here, and today we're going to be implementing k-means clustering. So I've looked at some of the implementations of k-means clustering with all of them having pretty much the same parameters, and looking at them I thought they were overly complicated, and so I decided to make this video to have like a more concise implementation, but it would support pretty much everything that those other implementations support as well. We can add some other parameters as well to what we're going to implement, but it's going to be more or less minimal implementation with the parameters that are absolutely necessary, pretty much. So we're going to do what is necessary for k-means. And now I already have the testing code prepared. I cannot really run this now because we have not implemented this yet, but I can show you the data, and this is how it looks. This is what we have before clustering. So it's one big cluster in a way. And so based on the value of k, we're going to cluster this data. If we say k equals 4, as we say here, that means 4 clusters. But we have to implement this first, otherwise it won't work, of course. Okay, so we imported NumPy, and from data classes, we're also going to import data class. Let's define class, call it k-means. And let's think about some of the parameters that it takes. It takes definitely k, as the name suggests, k-means. And we need to decorate this. We need some number of iterations, and we need tolerance, so that we know so that we don't do extra redundant iterations in if the tolerance value, if we pretty much have the mean tolerance, or if we reach the tolerance threshold. If we're lower than tolerance, we can stop, basically. And I'm going to show what that means, basically, here as well. The only method we need with the k-means is the fit method. And it takes some features, basically, which is the np-nd array. We don't really return anything. It's going to return none. And it's just going to cluster the data. Some of the things we're going to need are centroids and the closest. Closest is going to be like the array of closest values. Now, for initializing both the centroids and closest, we're going to need number of samples. And we can get that from the features. Now, notice that I don't really write it this way. We could have written it this way as well, but I don't really like magic numbers. So whenever I can, I avoid writing it, indexing with these specific number like 0, 3, like I don't really like that. So I like unpacking more, although we could have done that as well. And in some cases, indexing directly might make sense, but in this case, let's kind of make it, I don't know, it kind of looks more elegant in a way. So now we need centroids. For centroids, we can get the first k values out of the features directly, or the last k values, or the middle k values, but it's better to do randomization. To do that, we can use np random choice. We're going to make a choice out of number of samples with the size equals self.k with no replacement. We don't want duplicate features. And this one we can initialize as zeros with num samples. The next step is iterations. So we iterate we don't iterate over anything. We do iterations, self.iteration number of times. We're going to store the current closest array. And of course, the way k-means works is that we need these centroids, and we need distances for that, right? So we first need distances, and that's going to be, we're going to use a simple Euclidean distance, self.centroids, distance from centroids for every feature. We can compute it this way, and I think we're going to need axis 1. Self.centroids minus feature for feature in, we don't need self here, in features, because features are provided right here. Cool. Next, we need to update self.closest. And that we can do by saying np.argmin of distances, again along the first axis. Finally, we update the centroids. At index, we can do it this way. Features where self.closest is of that index, and we can do a mean of that. I believe it's going to be axis 0. Okay, and finally, if we can do like Euclidean distance again for comparison. if NP-Linac norm of self.closest minus old closest, if that is less than self.tolerance, we're going to break. Okay, and now I'm going to maybe explain more on how, elaborate more on how this is going to work. So explain more about the behavior of this kind of a function. So we define centroids. That has to be the number of sample, not samples, but the number of clusters, pretty much, the k, whatever we specify, and we take k features out of randomly out of the features that we provide, with no replacement. So we don't want duplicates in these features. We initialize the closest to the zeros, and we have these like centroids. Centroids, again, the center points. We iterate over self.iterations. We iterate self.iterations number of times, and then we save the current closest values, okay? Then what we do is we say, well, let's compute distances for every feature and the centroids. We then update the closest values. Closest values are going to be updated based on the distances, okay? In this case, centroids, those are going to be 4 values, and we do, this basically does broadcasting, okay? That allows for broadcasting, so that's cool, and we do it along the first axis, along axis 1. Then we take the closest values, again, closest from the centroids in a way, and we do it by using np.argmin along the first axis. Finally, we iterate self.k number of times from 0 to up to but not including self.k, so whatever from 0 to 3 if k is 4, and we say self.centroids at index is, we take the mean value across the 0th axis in this case. So features where the closest equals that index. Now remember that closest, that's like pretty much like the indices, because we do argmin. And then what we do, the only thing left here is, this is kind of optional, but it's kind of more efficient to have the tolerance value, because this allows us to see whether we converged, okay? And this tolerance value, that can be, that we can kind of fine tune. Alternative approach could be doing something like this. If np.array equal self.closest, old closest, we could break. So if the old closest, whatever we stored here, the reason we stored this again is so that we can then compare that to self.tolerance or self.tol, the tolerance value, or the alternative approach again is if the new closest values and the old closest, they are exactly the same, in that case we say we break, because if the closest values are the same, then the distances are and the rest is going to be the same. We're not going to have any optimization really happening, or any, the algorithm is just going to do the same thing over and over again. So we need to have that breaking capability. Now, of course, at some point we're going to run out of the iterations anyway, but having this is, helps, okay? But I think having this tolerance value is even better, because 2 arrays being equal, we may have some, in comparisons, we might have some floating point kind of problems where we compare, I don't know, 2.0 with 1.9999. Maybe it's going to say, I mean, if we have that tolerance, that already tells us, okay, we're close enough. With 2 arrays being exactly the same, that can be a bit kind of problematic. We may not get them to be exactly the same, but they might be very close. So now that we have this, we can go ahead and test the k-means algorithm, or the model. We set k equals 4, and there we have it. So before clustering, we have this one big cluster, and after clustering, we have 4 clusters. We have the blue, yellow, green, and this seems to be the purple cluster. Once again, we can configure things here. We set 10 iterations, so we can do more iterations, maybe 16. We can change the tolerance value to 1e minus 3, and maybe we can do 2 clusters. There we have it. We have 2 clusters now: the yellow cluster and the purple cluster here. Maybe we want 8 clusters. Can we do 8? Oh, we can. So now we have 1. So we have this kind of maybe a light green cluster. Then we have like a darker green. This is even darker. So there are three. This is like a bluish kind of a cluster, then like a maybe a light purple cluster, so that's 5. Then we have a yellow cluster, that's 6. This is the maybe like a dark purple cluster, and then we have like a again like a different kind of a green cluster, which is different from these ones. So we have 8, 3, 2, and 3. Super cool. And that's all we need for k-means clustering. We need how many lines of code? If we exclude the imports and this data class decorator, we have like what, 24 lines of code it seems. If we include this, it's like 25. So, well, it's actually 30 including the imports. So 30 lines of code, 30 lines of pretty much idiomatic Python. And we have like some of the primary parameters, or all of the like primary or main things that k-means should support. We have the k, we have the number of iterations, and we also have the tolerance, which is kind of optional, but it's kind of cool that we also support that. And that kind of, we handle it using these 2 lines. We store the old closest values, and then we use the tolerance to then see whether the Euclidean distance is less than that tolerance. So yeah, this is the k-means implementation, and that's going to be it for this video. I hope you enjoyed it. If you have any questions, please feel free to comment in the comment section, and I'm going to see you next time.